Hello, everyone, and welcome to Lab 10. In this lab, we're going to continue on exploring the analysis with t-tests, and we'll also introduce a two proportions test. Basically, the two proportions test is us going to be doing some calculation using R. So the first thing we need to do is we need to include some of the packages. So again, the library easy packages will do the trick, and then using that, we're going to also install the libraries ggplot2, activate the library ggplot2, psych, and tidyverse. Tidyverse also includes ggplot2, but just put it there just in case. Now, when I run this, make sure you also have created a new R code, which you need to save in the same directory as the one that you have your data. So go ahead and do save as and navigate to the directory. Here it's lab10. I'm going to save it as a code. And then don't forget to also go session, set working directory source file location. Okay, this way we let R know that the working directory right now is the same as the code. So when I run these two, it's going to tell me that all packages were installed properly. So let's go ahead and read in our code. We're going to be using a data set, which is the bench.csv. This data set contains some information about the bench press of various athletes before and after some training happened. If we look at this, it just has basically the gender of these athletes, the bench press prior to the training and after the training. And as we can see, we have 31 of them, some male, some female. All right, so what we want to do for starters is we want to try to figure out, some summary statistics for both. But let me also show you how one can arrange a data set like that. So for example, if you want to arrange it by gender, the command is basically arrange. This command comes from the package tidyverse, and I think it's the sub package to clear. And the only thing you need to say is arrange which data set by what variable. If you do it like that and you run, you will notice that the females go on the top and the males go on the bottom. So it's lexicographic ordering. If you want to switch that around, the only thing you need to do is the same code, but then use the DSC, so descending, to just basically just type that in. At some point, you should be able to type things rather than just copy pasting. So we are arranging the data set bench by the column gender, but I'm going to put descending DSC. All right, so when I do it like that, you will notice that the lexicographic order is reversed. And now my data set starts with the males and ends with the females. All right, so what I want to do next is I want to do some sort of descriptive statistics, but by gender. And to do that, we will use the function described by from the package site. And as you can see here, you just need to tell it which variable you want to analyze. This is the bench press prior to the analysis by gender on the dataset bench. So if I run this one, as you can see, I'm getting these two basically simple lines here, one for female and the one for male that has the summary statistics. All right. But what if I wanted to basically just do this real quick without any sort of grouping? Then there's the built-in command summary bench that gives you an idea about all the variables you should see over there. And again, notice that gender, it says, well, this is a character. It doesn't make any sense to look for minimum, maximum, and all that. But for the other two, it has it. But unfortunately, this one is not by the different groups. It's just like, here it is for the whole variable. All right. Now let's go ahead and try to do a little bit more, something a little bit more involving, which is basically split our data set into groups. And then what I'm going to try to do is I'm going to try to do some analysis, both for the females, for the males, respectively. So you can do that with the package tidyverse very easily. As a matter of fact, one of the reasons why I really like tidyverse, it's making all subsetting much simpler, and filtering is such a cool idea. So with this next line of code, I'm going to create a new data set, which I'm going to name bench M by starting with the data set bench and filtering in the column gender to be equal to M. So basically, when I run this, you'll see that I've created a new data set, bench M. If I click on it, it only has the males here, right? So the way it is written is start with this data set and filter it, make sure that the column gender is just equal to M. Notice the two equalities here. This is a little quirk that R has. When you say logical equality, you need two equal signs. And similarly, you can just do the same thing here and create a bench F. All right, but I start with the same data set and filter by gender equals female. So if I run this one, you'll notice now that I have a data set only for the female. All right. There's another way that you can get there because these two are complementary. You can just do the same thing. Bench F is equal to bench. And then notice this little pipe thing. This is amazing. So you start with the data set and you apply something to it, like a pipeline type of thing. And you can filter the gender column being not equal. Note how we write not equal, it's an exclamation mark and equal to M. This is also going to create the same bench F, right? So there are various logical arguments you can put here in the filtering. In any case, that's how you create the two data sets, bench F and the bench F. Those two are completely equivalent. So now, one thing that we might want to do is we want to try to figure out if the bench press has changed before the training and afterwards, right? Let's do it first for the female, and then we'll figure it out for the male. If you look at the summary statistics that we had before, you see that for the females, the average bench press was 46.92. So if we want to figure out if the post-training bench press for the females has changed, we can look at this as a one sample t-test where we take the bench press new for the females only, and we'll try to see if this is the same as 46.92. So we could theoretically create a hypothesis test where we say the average maximum bench press before and after the program was not changed, and the average maximum bench press before and after the program has changed. Again, we don't necessarily know which one is better, but in this situation, we could put that the average maximum has increased. And the idea is, well, we're doing all this training to become better at bench pressing, right? So if there was a change, it would have been one-sided towards a bigger value. So yes, you can actually change this into a one-sided t-test, all right? And as I said, one way to do it is to see, like, is this the new bench press new column on average different than the initial average for the female? And you can do that by using, again, the function t-test. And you just need to tell it which column you're looking at, and you're looking at the column bench press new of the data set bench F, right? So bench F $sign, this takes you to this variable of this data set, and you're comparing it to the average value for the 6.92. That was the average value of the bench press for the females prior to the training. And this is what we want to do. A one-sided, we'll put greater, right? So this is not going to do the two-sided test, it's just going to do the one-sided. If I run this line of code, what I'm getting here is I'm getting a p-value of 0.009762. If I was to look at this, I'd say, well, p-value is much larger than 0.05. Not enough evidence to suggest that there is a difference, okay? And here might be clear why we say it like that. It turns out that this is actually not the right test. Although we might think, well, that seems reasonable, this is not the right test. And so you're not supposed to use this one to basically compare what we're trying to do. What you really need to do is you need to look at the bench press before and after for each individual athlete, all right? So basically, we're looking at a pair t-test here. In order for you to be able to do that, you need to use this line of code where basically you're saying compare the bench press before, which we just noted as bench press, with the bench press new on the data set bench F, right? And then paired equals true, makes sense, right? Because each person is measured before and after, and we know which one is what. And this is a more appropriate test than the previous one. When I run this test, so now the p-value is 0.001035. And as a matter of fact, we need to even like half this one because by default, this is a two-sided test when we're looking at just a one-sided test. In any case, the p-value now is much smaller than 0.05, so we definitely reject the null hypothesis. There is enough evidence to suggest that there's a difference between the bench press before and afterwards for the female athletes. Okay, so with the initial test, when we fail to reject the null hypothesis, we don't really accept it, right? And that's the reason. This was not the right test to do so. This is the right test to do so. And with this right test, we actually reject the null hypothesis. Okay, that's why we're diplomatic when we fail to reject the null hypothesis. One of the reasons could be like we're not using the right test. Okay, so once again, that's how you test the paired t-test, right? And again, the p-value is exactly half of that. So now that we're using the appropriate test, we reject the null hypothesis. All right. Now, the rest of the section is exploring the idea of two proportions hypothesis test. There is no real statistical test inside R that will do this for us, but we can use R as a big calculator, basically. So in this situation, I have in an older survey, we had 270 college students that were asked the questions, do you prefer vanilla or chocolate flavor ice cream? And then in that sample, we have 149 male and 121 female participants. And 34 of the male participants and 67% of the female participants said they prefer chocolate and the rest vanilla. All right. So then we want to see if the proportion of preferences amongst the female students is the same as that of the male students, right? So let's say the proportion of people that prefer chocolate is the same as the one as vanilla, or do it the other way around. It really doesn't matter, right? What you need to test here is whether or not these two proportions are equal versus the alternative is whether or not these two proportions are not the same. What we're going to be doing is we're going to be doing, as we said in class, a two proportions Z test, and it's going to be two-sided because I said here different than. All right, and everything that we need is there, and we will be utilizing the central limit theorem for the standard error that we don't have. And what we need to check is basically independence, between and within those they are given. And then we have that other condition that I mentioned that we need at least 10 observations in each subcategory. So basically, male and chocolate, in this case, is 34 greater than 10, male and vanilla, 115 greater than 10, female and chocolate, 67 greater than 10, and female and vanilla, 54. And again, that's greater than 10. So all categories have more than 10 observations. And that 10 is like a little bit of a heuristic. We've discussed that in class. That's how you check it though, right? So some sort of like easy check of the numbers that are there. Okay. So another thing that we need to notice is that the two groups don't have the same number of participants, which is fine. Okay, this is an unbalanced set, but it's okay. Like the number of female students, female students is 121 and that of male is 149, but these two are comparable, right? It's very easy to do all this if you start including things in R one by one. So let's name NF the number of observations for the female and NM the number of observations for the male. Let's run these two, and as you can see, these values are now in R. And then what we want to figure out is what's the proportion of people that want chocolate, for example, for the males and the females respectively. And so that is, let's call it PM. That's going to be the proportion of males. And that's going to be like 34 divided by 149. And that for females, it's going to be PF, and that's 67 out of 121. All right, and as you can see, the PM is 0.22, the PF is 0.55. I'm pretty sure there's going to be a difference here, but let's also prove it statistically. Then what you need to do is you need to compute the standard error. And remember, in class, we learned that the standard error when you have two proportions is given by this formula. It's sort of like blended average between the two proportions. Each of them came again from the central limit theorem. So here's where SAS and R can come in handy. You can just type this one in, and as long as you have introduced these variables in the past, this should work just fine. Let's make sure that we're copying it right. Okay. And so it's this, right? It's the square root of this product divided by NMN and by number of observations of them, and that for F, and big parentheses for the square root. If you run this, you'll see now that you have the standard error right there. Okay, and remember the computation is just a simple z-score. It's the difference of the two proportions divided by standard error, but standard error computed this way. And again, I'm going to save this as z. There. And when you run it, here's your corresponding z-score, 5.7. I'm pretty sure this is going to give us a very, very small p-value. And to get that p-value, you just use the command p-norm on that z. Don't forget, we're doing a two-sided test, so we need to find the probability above that value that we got. So that's going to be 1 minus p-norm z. and we need to double it because we're doing a two-sided test. So when we run this, you get a probability which is very, very small. As you can see here, it's 9.87, but that's multiplied with 10 to the minus over 9. So you measure like 0.00010 of 9 of these, and then 984. So this is practically nothing, right? And that's what we say. Our p-value is extremely small, and so we reject the null hypothesis and conclude that the sample proportion, that in this sample, the proportion of female students that prefer chocolate is statistically significantly different than the proportion of male students, all right, in this sample. And I'm not really using any sort of test here. I'm just using R as a calculator, okay? But it's just that you can do it a little bit faster, all right? Now, this concludes Lab 10, and again, straightforward stuff. The t-test is a very interesting, very simple process, one-line code, but you need to be able to figure out what is the right test, all right? That's more important than just what the code is. Okay, that's all for today. I'll talk to you on the next one.